All right, so welcome to our webinar on optimizing code performance. I'm Kylie, your host for today, and we're joined by Daniel. Daniel is a Microsoft MVP from Particular Software. Now, Daniel is an expert in improving .NET message-based systems, and he'll guide us on using BenchmarkDotNet for performance improvements and share insights on cost-effective optimization. A Q&A will follow, so ask your questions, like I said, in the Q&A section. All right, Daniel, it's all you.
Hey, Kari, thanks for the warm welcome. Hi, everyone that joined us today in this webinar Beyond Simple Benchmarks. Like Kari said, I'm Daniel Marbach. I'm from Switzerland, and we're going to be presenting to you about this very interesting topic. And I saw the poll already, so we have quite a few people that are new to sort of benchmarking and performance optimization. So that's great. I think then this talk will even be more relevant to you. If you have also any questions that I cannot sort of answer in the follow-up, so you would like to reach out to me over social media, you can reach out on X under my name, or you can send me an email on the daniel.marbach@particular.net, or you can also find me on LinkedIn should you wish to connect there. And I'm happy to follow up with you as well. So I remember sort of the first time I started benchmarking my code changes to verify whether the things that I thought might accelerate this code really made an impact. I had already seen quite a few benchmarks similar to this one that I'm presenting on the screen that were written in BenchmarkDotNet. I saw them on blog posts, on sort of open source projects. And by the way, don't bother to look too much at the code because the code is not really that relevant that I'm presenting on the screen because I didn't either at the time. So I was just like conceptualizing BenchmarkDotNet as sort of like a unit test, right? Because my conceptual understanding was like, oh yeah, it's right, like a unit test. I've written quite a few unit tests with X unit, N unit, and God forbid MS tests. I'm sorry for those that have to use it. I had to use it as well. I feel you. But I was like, okay, I felt quite certain it wouldn't take me too long to actually get started with this BenchmarkDotNet and actually doing benchmarks. But I was horribly wrong. I mean, writing the skeleton of the benchmark was indeed very simple. So the mind-boggling part for me was trying to figure out what should be taken into account in the benchmark, how to isolate the code without basically spending crazy amounts of time in refactoring the code to actually make it even possible to benchmark it. What should be deliberately cut away to make sure the changes that I envisioned are going in the right direction, because that's important. I want to know where I'm heading to, right? And how to measure, change and measure without burning away the allotted budget, right? Sometimes I've been doing these in my sort of my free time, and my allotted budget in my free time is smaller, but even in sort of professional environments, you can't just go and sort of close yourself into the cellar, ignore all the customers and do these types of performance optimizations and benchmarking like all the time, except if that's your job. But we rarely ever are in the sort of the profession, right? We need to deliver code that actually makes a business impact. But then the question is, why would I even bother and go through all this hassle, right? Because we've already talked about that we only have a limited budget usually available. Well, the thing is, for code that is executed at scale, the overall throughput and memory characteristics are really important. Because code that wastes unnecessary CPU and memory cycles ends up eating away resources that could be used to serve requests. And especially with modern sort of cloud native approaches, even if you're not there yet, if you're sort of planning to migrate to sort of cloud native, or you have your own data center, you want to make sure that essentially these resources are used as efficiently as possible. And for scalable code like that, it's even more important that we are sort of making sure that we are using these resources as efficiently as possible. In the cloud, we usually sort of get built by the number of resources consumed, right? And the more efficient the code is, the smaller the bill, right? And the more requests we can execute for the same amount of money, essentially. And let's not forget, more efficient code execution also means that we are consuming less energy, which is important, an important cornerstone of the green IT sort of movement as well. Or let me give you an even better example to quote Microsoft. So Microsoft has sort of a blog series where they sort of talk about the teams that are migrating existing infrastructure that is, for example, running on .NET Framework to modern .NET versions. And I have here one quote from the Microsoft Teams infrastructure and Azure Communication Services journey to .NET. And the quote there is, we're able to see Azure compute cost reduction up to 50% per month. On average, we observe 24% monthly cost reduction after migrating to .NET 6. The reduction in cores reduced Azure spend by 24%. And the performance improvements that they got by migrating from .NET framework to .NET 6 to leverage sort of more modern C# programming technique and memory efficient code and also CPU efficient code, they got like 30 to 50% improvements in performance, including sort of the P99 CPU utilization and sort of P99 service latency. And that's quite amazing, right? Because just by sort of leveraging these techniques. And in this talk, I have summarized my personal lessons on how to make performance optimizations actionable. I will show you also a practical process to identify some of the common bottlenecks, isolate components and measure change and measure without breaking the current behavior. I have to warn you though, I will not cover all the knobs and dials of BenchmarkDotNet. I will also not cover mechanics of using profilers, although you'll get a fair number of insights into the analysis process of understanding some profiler output. But let's not waste more time. Let's get into the essence of the talk. So for me, one of the key principles I try to apply to almost everything in software is making explicit trade-offs and decisions as we go together with the teams that I'm working with. This also applies to performance. And I would say a reasonably mature team should be performance aware. Or as my friend Martin Bayou from Belgium once famously said, in some countries, you have to be bear aware because, for example, when you're hiking in Canada, it's good to be prepared for the likelihood of a bear crossing your hiking paths, right? Not so much though in Switzerland, where I live. I guess we have some wolves, but I definitely don't, I'm not aware that we have bears, but I'm completely digressing here. That's not relevant for the talk. But when it comes to performance, when you're performance aware, it doesn't mean you have to always go all the way in, not at all. In fact, I myself always start with the simplest solution that just works first, and then I get some reasonable test coverage in place. Once I have a working solution with a good test coverage, I start asking myself questions like, for example, how is the code going to be executed at scale? And what would be the memory characteristics of this code? And that can be just a gut feeling based on my sort of more than 10 years of experience in writing .NET code. Then the next question that I ask myself is, are there simple low-hanging fruits I can apply to accelerate this code? Then are there things I can move away from the hot path by simply restructuring a bit my code, right? Because everything that I don't have to do on the hot path is actually something that doesn't impact my hot path. So that's always a good question to ask. Then my question is also, what part is under my control and what isn't really? So for example, sometimes I'm only owning parts of sort of the stack that is in place in a specific code path. Sometimes another team owns it, or sometimes I have to interact with a third-party library that is not under my control that I can't contribute to, right? Because it might be closed source. If it's open source, I might be lucky because then I can go there and maybe contribute if that turns out to be the culprit of the code that I'm looking at. But I have to be aware of sort of the boundary conditions around my piece of code that I'm looking at. And then last but not least is sort of what optimizations can I apply and when should I stop, right? Because these types of performance optimizations can get very addictive and I have to always find the right balance in order to sort of make sure that I'm using the time that I have and everything else involved as efficiently as possible. And I have covered some of these nuances further in my talk, Performance Tricks I Learned from Contributing to the Azure.NET SDK. You can look that up on YouTube if you're interested to hear more. But then let's put that aside. And once I have a better understanding sort of the context of the code by asking these questions that I just showed you, depending on the outcome, I start applying the following performance loop. So the performance loop is something that I came up with based on sort of my experience of doing performance optimizations. And I feel it's a great mechanical approach to apply performance optimizations in a structured way. And what I do is I usually start with sort of profiling first. That's the entry in the performance loop. I write a simple sample or harness that makes it possible to sort of observe the component under inspection with a memory profiler and a performance profiler. So the profiler snapshots and the flame graphs that I'm seeing there give me sort of an indication of the different subsystems at play, allowing me to make explicit decisions on what to focus on and what to ignore, right? And then once I have a good understanding of the code that I have in front of me, I can start improving it. I usually select the hot path, for example, the one that is responsible for the majority of the allocations or the majority of CPU time spent, or the biggest slowdown, in other words, or where I feel I can make a good enough impact without sinking days and weeks into it. So if the code path in question is not really well covered with tests, I usually get test coverage in place first before I start doing any sort of improvements, because it doesn't really help if the code is extremely fast, but utterly wrong, right? And then I start experimenting with the changes that I have in mind and check whether they pass the tests that I have in place. Once it functionally works, I put things into a performance harness. And then I can start sort of benchmarking. So what I usually do is to sort of save time is I extract the code as well as possible into a dedicated repository. And then I do a series of short runs to see if I'm heading in the right direction. Once I'm reasonably happy with sort of the outcome, I do a full job run to verify the before and after. And that is sort of a rinse and repeat, or what I call the inner loop, right? Because sometimes I'm learning more about the code and I see, oh, I can do further tweaks. I put it back, I do some improvements, put it back into the benchmark, and then I sort of go back and forth there. And once I'm done, I'm actually not done yet, right? Because what I do then is I sort of profile it again with the harness that I wrote earlier and make sure that sort of the code that I optimized and benchmarked in the benchmark scenarios actually leads to the things that I want to see by using the test harness again. And once I'm then reasonably happy with it, I ship the code and focus my attention to other parts of the stack. So what I can do is I can go further down in the call stack, or I sort of go into other components and focus my attention. If I still have budget to sort of work on performance optimizations, I can then focus on other parts on the system. But enough of this overview of the process. Let's dive into sort of a more practical example. Because I work for particular, I'm going to sort of cover that with answer response. So answer response is the heart of sort of the distributed systems and is part of the particular service platform. It helps create systems that are scalable, reliable, and flexible. It's sort of an abstraction on top of sort of message-based systems. It can integrate with Azure Service Bus, storage queues, SNS, SQS, and it allows you to sort of focus on your business code. If you want to learn more about Answer Response, if you're new to it, you can go to go.particular.net/webinar-2023-quickstart. But at the heart of Answer Response is sort of this, what we call sort of the Answer Response pipeline. And that's the most critical infrastructure piece inside Answer Response, or an Answer Response endpoint that consumes messages from the queue. The pipeline is the engine that makes sure all the required steps involved, like serialization, deserialization, transactions, database access, sending and receiving messages, are executed as efficiently as possible. And as such, it's very crucial for the pipeline to not get in the way of the customer's code. And as we can see here on the screen, the pipeline, when it pumps sort of messages from the queue, it has a set of behaviors that sort of sequentially executed against each other. And the behaviors are essentially the things that we are sort of plug in the necessary infrastructure pieces, but also customers can plug in their parts to the pipeline to sort of extend it in a sort of open close principle way, what Answer Response does. And if you're not familiar with behaviors, you can conceptualize it similar to ASP.NET Core middleware. So ASP.NET Core has sort of a middleware structure, and I have here an example of a request culture middleware where you sort of have a class that has a method called invoke async, and that method gets a context in, and it has a next delegate where you pass the context on to the next sort of middleware of the ASP.NET Core. And in Answer Response, those behaviors are actually extremely similar. And let me show you that. So we essentially have a class that sort of inherits from behavior, and it defines a stage. It's here called incoming logical message context. There are multiple stages. The logical one is where the message is already deserialized. There is also the physical stage where the message is not yet deserialized. And essentially the heart of the logic is sort of happening there. So what we do there, for example, we sort of find out what message type you're getting, we deserialize things, then we sort of get from the IOC container sort of the customer code, we sort of call it, right? Then we have integration with Cosmos DB, SQL Server, DynamoDB, Entity Framework, and Hibernate, and so all sorts of sort of IO-bound systems. And there are also bits and pieces that create open telemetry traces, logs, and much more, right? So in order to sort of get an understanding when we have to look at the pipeline and how we can optimize it, we sort of can do that by actually doing profiling, right? And that's the first thing before we even go into benchmarking. So to get a good overview of the problem domain in front of us, it's vital to create a sample or a harness that allows us sort of to zoom in into the problem space. And again, since my goal is to optimize the pipeline invocation, I can look at the pipeline invocation with a tool like .trace from JetBrains to get a good understanding of the performance bottlenecks and analyze the memory usage with a tool like .memory. I always recommend to look at multiple aspects such as memory, CPU, and IO involvement to get more insights from multiple angles. And by the way, I'm mentioning the JetBrains tools because I'm a big fan of the JetBrains tools, but you can also use your favorite other tools. There are multiple on the market. You can even use the Visual Studio built-in stuff if you have access to that part, depending on your license. So your mileage may vary there. So what I did there to set up a sort of a harness that sort of makes sure that we can sort of look at the pipeline invocation, I created this small application. It's here on the screen. So first of all, I essentially set up answer response in a way, and I configured MSMQ transfer because on Windows, that's sort of the simplest thing. It's already built in. It's super fast because it's local. And I used that at the time to sort of profile the pipeline. Then the next thing I'm doing is I'm using a serializer that is quite fast. I'm using JSON serializer, system text JSON serializer to not get in the way, to sort of not skew with stuff that I'm not really interested in, sort of in this test harness, the picture. And then what I'm also doing is I'm adding an in-memory persistence because I do not want to see any sort of SQL transaction stuff because it's just noise for the thing that I'm looking at. And then what I'm doing is I'm publishing 1,000 sort of messages with answer response. And then what I'm also doing is I have in this sort of test harness, I have a bunch of console read lines that sort of are interaction points where I can attach the profiler to say, okay, now answer response is started. Now I can sort of take a snapshot, and then once I have published, I take another snapshot so that I have multiple sort of points where I think like, okay, there is something relevant happening where I want to see what's going on, right? And then what I also put in place, a handler that sort of gets all those 1,000 messages that I published. I have here also a console write line. Normally, I would advise you to not do a console write line because it also skews the picture slightly. I added it to also make sure that the test harness actually works, right? Because again, if the test harness is already wrong, we're sort of going in a direction of not so optimal path. So we want to make sure that everything works as well. And then usually a good test harness should adhere to a few things that I have here on the screen. I'm sorry for that thing. So usually what you should be doing is they should be compiled and executed under release mode. It sounds super obvious, but I'm mentioning it here because the amount of times I actually have forgotten this, it's staggering. Then it should run a few seconds and keep the overhead quite minimal. Then you should disable the tiered cheat. Cheat is the just-in-time compiler to avoid sort of any sort of warm-up. So you need to add this tiered compilation to false into your CS proj. And then usually what I also advise is because by default, if you do a release mode, you don't get sort of the full symbols. And then add sort of the full debug symbols so that you get a good picture over the stack traces and everything involved should you want to have a closer look at it. So that's sort of the general thing that a good test harness should encompass. Good. Then the first thing that I'm doing is I'm looking at the memory allocations because allocations usually have a big impact on the throughput of the system and can usually be optimized up to a certain point with a few quick wins without unnecessarily increasing the complexity just yet. This often comes from the fact that many systems have not yet been optimized for memory allocations. And sort of to understand the data that is presented in front of us, we require usually domain knowledge of the problem at hand. And that knowledge sort of helps us to navigate through the maze of noise that we might see. And as we can see here on the screen, there are numerous of sort of byte array, memory stream, and stream writer allocations that are quite hefty. But we are interested in the pipeline execution, remember. So when we zoom in, we can actually see that 20 megabytes of the pipeline are coming from this sort of behavior chain invoke next thing. Now, the question is, are we done yet? No, because this is just the publishing part of the pipeline where I'm actually sending messages. And remember, I send 1,000 messages in the test harness. Now, we want to look at sort of the full picture also on the receiving end. If you look at the receiving end, when the messages are coming in, we see also, again, lots of byte array, XML text reader nodes, and message extension allocations. But again, now, because we're looking at the pipeline, we sort of have to blend out this noise and look at what is actually coming from the pipeline. And using my domain knowledge, I know that this funk of behavior context of task allocations are coming from the pipeline. Good. We have another 27.83 megabyte of allocations that are potentially unnecessary that we might be able to get rid of. Then what I also usually do is I look at the stack trace. And here I have an example of the stack trace. It's pretty massive. It contains plenty of steps that actually clearly hide the actual pipeline operations, like the mutate incoming transport message behavior or unit of work behavior. And for you, conceptually, if you're not that too familiar with answer response, you have to think about it. That's the actual business logic that we sort of plug into answer response. And that is not really visible because the rest, as we can see here on the screenshot, we have this behavior T context, behavior invoker, behavior chain display class, and blah, 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 until actually we see the unit of work behavior. And sort of the in-between stuff is basically just noise. It's infrastructure stuff that sort of enables things, but we might be able to get rid of it. And then the question is also, when I showed you previously sort of these allocation screenshots where there were like lots and lots of byte array allocations that were heftier than actually these 20 megabyte and 27 megabyte of allocations that were actually coming from the pipeline. And you might be thinking, but Daniel, I mean, come on, all this gymnastics, why aren't you getting rid of these allocations? Should you do that, right? Because they're super hefty. And yeah, technically, ideally, yes, we would actually want to get rid of all the other allocations that are sort of heftier in this picture. But in this specific case, there are actually a few things we have to consider. So the context really matters about the piece of code. And the context is super crucial when we look at these sort of profiler screenshots or profiler outputs, sorry. So for example, in our case, the allocations that we saw, they're mostly coming from MSMQ transport, which has a diminishing user base. Most users eventually transition away from MSMQ to either SQL Server, RabbitMQ, or in the cloud, transport like Azure Service Bus, Amazon SQS. So our efforts there might lead to allocation reductions only for a very limited segment of our user base. Another angle could, for example, be that we might not be transport experts, right? We already know by making iterative gains on the hot path, we will end up with great improvement, sort of the 1% improvement philosophy, right? But since every activity has to be weighted against building features and all the other activities that we're doing in our day jobs, it might not be justifiable right now to ramp up the knowledge in that specific area. And then finally, our goal is to see what we can do to optimize the pipeline, because the pipeline optimizations have a great benefits for all the users across the board in the specific example of answer response, right? Independent of the transport. So then let's have a look at more allocations that are happening here. What we can do is we can sort of zoom in more into the pipeline. And what we can then see is we have sort of a lot of behavior chain, function tasking, funk of behavior context, and display class allocations that are so totally unnecessary. And with a tool like .memory, what we can also do is we can filter the view to a specific namespace. And when we do that, we can see all the allocations that are coming from sort of everything that is in a specific namespace. And here is the answer response.pipeline namespace. And then last but not least, like I said at the beginning of the talk, it's usually not enough to just look at one type of a profile, right? We also have to sort of, so it's not enough to just look at the memory profile. We also need to look at the CPU profile, because sometimes any algorithm that spends a lot of CPU cycles executed on the hot path can also have a significant impact on the performance. So, and flame graphs are an extremely helpful tool to actually get a very quick understanding of what's going on. So let's take a look at the CPU characteristic of the publish operation in a flame graph. And I have it here on the screen. And for you, I know this might be a little bit overwhelming, but actually, when you look at the top of the flame graph, we can see there's this message session publish, and we read the flame graph from top to bottom, right? That's what we're doing. That's the arrow on the left side. And what's great about the flame graph is that we can actually, without having a big understanding of what's going on, we can actually quickly understand what's actually where it's spending time and where it's not. Why is that the case? Well, with flame graph, what's actually happening is each call is shown as sort of a horizontal bar whose length depends on the call's total time, which equals to the function's own time that's executing, plus the time of all its child function being executed underneath, right? So the longer the bar, or the longer the call, the longer the bar is, right? So that means we can have a look and we can see there's also all sorts of red stuff happening on the screen, and there's some orange stuff on the side. And the red stuff, based on my domain knowledge, I can see there's actually the infrastructure part that might not be that relevant. And sort of the orange part is the actual sort of IOC container stuff, integration, the thing, or the actual business logic code that is being executed, right? So, and if we zoom in into sort of the flame graph, we can also actually see that. We see that there is the mutate outgoing message behavior, and there's lots of stuff going on in between. And then again, at some point, we then deep down sort of the flame graph, we actually see the actual business logic being executed. And this is the flame graph that also comes from sort of the JetBrains tool. By the way, if you prefer using free tools, and for example, you're running on Windows, I can highly recommend to use a tool called PerView, which gives you very similar results in more recent versions. You can also zoom in with PerView. I have here the same picture visualized with PerView. This time, unfortunately, it's bottom up. So the actual publish operation starts at the bottom. And as you can see here, it's a little bit of a sort of a overwhelming tool potentially. I think it's quite an advanced tool. There's numerous of great articles, blog posts, tutorials, and videos available to get a better understanding of PerView. I personally have used it, but I struggle sometimes to put in all the right commands into the text fields, and I usually prefer to go another tool, but your mileage may vary. Just for those people that are thinking, Daniel, you're clearly a fanboy of the JetBrains tools, right? It's like, yeah, it's right. I am a fanboy of those tools, but use whatever gets the job done and what you prefer, right? Because your mileage may vary. Okay, and then again, if we're going back to the tools that I prefer, we can see that when we look onto the hotspots overview filtered into the publish operation, we can see that the behavior chain is consuming 20%, and the behavior invoker is consuming 12.3% of the CPU, which is a third of the overall time spent executing the mechanics of the pipeline. On the receive end, the picture is slightly less dramatic, but there's still a measurable impact if we look at the CPU characteristics. What we can see there is, again, if we're sort of zooming in and we're looking at the hotspot view, we can see that the behavior chain is consuming 4.8% and the behavior invoker is consuming 9.2% of the CPU, which is sort of a seventh of the overall time spent executing the mechanics of the pipeline. And now that you have seen the flame graphs, you might be wondering, but Daniel, what about flame graphs? Well, I have them for you. Again, we're reading from sort of top to bottom, and now we are in the receive parts of the pipeline. We can actually see on top, there is this receive transaction scope, receive with transaction scope, receive message, reading top to bottom. And again, the same picture of the infrastructure overhead becomes apparent in the receive pipeline by only glancing at the flame graph, right? Because we see, again, lots of red stuff, and then we have sort of the orange yellow part on the other side, which is sort of the actual business logic that is being executed, which is way smaller, right? And now we are ready. Well, let's have a look at sort of zooming in. When we look at this, we can actually see again the same picture on the receive end. We see the mutate incoming transport message behavior, lots of infrastructure pieces, and then we see the actual business logic being executed way underneath, and sort of the relationship between those things are way off on the infrastructure side that hopefully we can get rid of. So now that we understand the memory characteristics, the CPU characteristics, and if you're working with an IO-bound system and you want to look at sort of what is the IO characteristics, you should also look at IO profilings, and some tools can actually do that. For the interest of time, because we only have a limited time in this webinar, I'm not covering this. I'm only covering the CPU and the memory characteristics. And I also believe that looking at CPU and memory gives you lots and lots of great indications for doing your optimizations. Then we can actually go to improve things, right? Because that's what we want to do. We want to change the code to make it faster, but hold on your horses, right? We actually want to get good test coverage in place. If we don't already have it, right, then we have to write it at least at this specific point in time, because we need to sort of take our context, take the domain knowledge, and put tests in place to make sure that our sort of improvement cycles are not invalidating what's already there and are not breaking the things, right? So that's crucial. So luckily with the Enterprise Plus pipeline, we already had sort of lots and lots of acceptance tests in place that were sort of executing the system end to end. But there were a few tests missing, specifically what I call component tests. So basically the idea of a component test I had in mind there was to just take the pipeline and only execute the pipeline with the relevant parts, but not the rest of the system, to make sure the pipeline actually does what it's supposed to do. And I wrote a few tests, like it should just execute the pipeline. And for example, there were a bunch of state objects that were sort of passed into the pipeline. I added a test to make sure that nothing sort of gets statically cached that shouldn't be statically cached, to make sure that the thing that I'm now start tweaking actually works as it is intended to work. And then I start making improvements. And so if you're interested, in the interest of time, I'm not going sort of deeper in the actual improvements that I did, but I have a bunch of blog posts available on the particular blog. You can go to go.particular.net/webinar-2023-pipeline. There's one blog post called 10 times faster execution with compiled expression trees, and how we achieved 5 times faster pipeline execution by removing closure allocations. And basically the gist of it, I did a bunch of sort of allocation optimization tricks that removed all sorts of allocations that we saw on the previous screenshot. And that sort of gave us a 10x boost in the first iteration, another 5x boost. And in the third iteration, even another 20% boost in terms of throughput of the raw execution speed of the pipeline. But I know these are very clickbaity titles, but I hope you enjoy these blog posts should you wish to dig deeper into sort of what I did there, because that's not really relevant for the webinar today. Good. Now let's look at the benchmarking the pipeline. So usually with code that we have in place, right, if you're lucky, the thing that you want to benchmark might be a public method on some helper or utility without countless external dependencies. Then everything is golden, right? Because then it's mostly simple, because you can just basically add a benchmark project into your solution, reference the assembly in question, and then start calling this method. So in the worst case, you might need to add internals visible to give the benchmark project access to this helper or utility. So much about the theory, right? Because in practice, software is way messier than we like to admit, at least the software that I'm usually working with, or even worse, that I have created, right? So because components sometimes come with numerous dependencies. So we can bite the bullet and just throw them all under a benchmark. But then the gains that we are trying sort of to compare might get lost in the signal to noise ratio, or how Gordon Ramsay would say, software is a disgusting, festering mess, right? So when I first started to face this problem, I started looking at various approaches and ended up with a very pragmatic, potentially slightly controversial approach. The pragmatic approach that I took is I was copy-pasting the existing relevant pipeline components, and I adjusted the source code to the bare essentials. And this is how it looked like. I'm going to present it to you on the screen. So this basically allowed me to isolate the component under inspection. That's the pipeline stuff. That's on that folder that you see in that pipeline folder. And here we have a bunch of classes, behavior, chain behavior instance, behavior invoker, step coordinator, and whatnot. For you, don't worry about these names. These are just fancy names to basically describe the mechanics of what's going on. And as you can see, it's not just a simple class, it's not just one method. It's actually multiple classes and things that are sort of behaving and coordinating things with each other to actually execute the pipeline execution logic. And the idea sort of there is that we want to make sure that we have a controllable environment that is only progressing when I adjust the code that I have copied with sort of the copy paste sources that I took from the pipeline. What's also cool with this approach is that I can tweak the code with, for example, partial classes to be able to easily overload relevant aspects that I'm tweaking and then execute different approaches against each other to make sure I select the one with the right trade-offs. And again, I want to highlight this approach worked very well for me, and I think there is great value in others for it. And to give you a more concrete example with the pipeline, for example, what I started doing is I started trimming down the pipeline to the only relevant behaviors that were relevant for my benchmark. So I removed everything that I felt like is not relevant for the pipeline execution. And then, for example, what I also did is I removed the dependency injection container with creating a relevant classes to basically just new them up in a hard-coded way for that specific scenario. Because again, I'm not interested in comparing different IOC containers that are out there. Right? That's not my job. I'm looking at sort of the pipeline execution and how I can make that part faster. Then I already explained to you, there's lots of sort of, usually in a real Ansible system, there is lots of IO going on because we access databases and we do transactions and whatnot. But again, for the raw sort of pipeline execution speed, I can actually sort of remove that noise and just return it with a completed task. Since the IO operations, they're hundreds of thousand times slower anyway. And again, our goal is to sort of optimize the raw pipeline execution. So we need to remove them. By the way, some of you that might be more advanced into sort of the whole async land, they might be thinking, yeah, but Daniel, I mean, you're not tricking me. I know the task completed task, it just returns a completed task, and therefore there's no yielding happening with the asynchronous state machine. Isn't that actually skewing the results? I'm going to talk a little bit more about BenchmarkDotNet and what it does, but the gist is basically because how BenchmarkDotNet actually executes things. If we would basically do a task to yield with its statistical analysis and running it for a period of time, those things would actually blend against each other. And for this specific scenario, it's actually totally okay to just use a completed task. But again, context is the key, and your mileage may vary depending on the scenario that you're looking at. Good. That being said, I would like to say, because I said it's a controversial approach because I'm copy pasting code, right? I would say apply the sort of 80-20 rule. For code that is not changing that often, this approach works very well and gets you started sort of tipping your toes into becoming performance aware quite quickly without sort of overwhelming the whole organization of sort of building up a performance culture, right? Because remember, doing cultural changes in an organization takes time, and you rather want to make changes gradually. And you might be coming as sort of the first person that is doing these performance optimizations in a structured way. You might be becoming the go-to person, right? And you also don't want to overwhelm yourself. And then there's also things like, with this approach, you actually are not you're not facing yourself or the organization with questions like, how can I reliably execute those benchmarks? How can I set up the CI/CD pipeline? What do I need to take into account? Do I need to have dedicated hardware? Can I run it on GitHub Actions or on my DevOps runner? Is that good enough? Or do I need specific images to actually do that? And all sort of those mechanics that you would be coming, it's like further down the pipeline of sort of becoming performance aware, you can essentially blend them out and get started building this performance culture without overwhelming yourself and the whole organization. So that's sort of the key message that I want to give away. So I have here a benchmark on the screen. And again, at the beginning, I sort of said, my conceptual understanding was like writing a unit test. But the thing is, they're actually not the same, right? Because when we write a unit test, We ideally want to test all methods and properties of a given type. We also test both the happy and the unhappy path. And the result of every unit test is basically a single value. It's either passed or it's failed, right? It's red or it's green, right? But benchmarks are completely different. So first and foremost, the result of a benchmark run is never a single value. It's always a whole distribution described with values like mean, standard deviation, min, max, and so on. And to sort of get a meaningful distribution, the benchmark has to be executed many, many times. And this takes a lot of time depending on the problem that you're looking at. So the goal of benchmarking is to test the performance of all of the performance of methods that are frequently used on the hot path, right? And only those methods should be performant. So the focus should be on the most common use cases and not on edge cases. But how do we find those hot paths and the most common cases? With the pipeline, one obvious case is sort of the pipeline execution. And what we can see here is that sort of when we do the raw pipeline execution, we first do a global setup with BenchmarkDotNet, and we put sort of building the pipeline into the global setup. Why the global setup? With BenchmarkDotNet, it actually makes sure that this is sort of executed once before all the iteration. It's not sort of counting to sort of the statistical analysis of sort of the runs. And then we can sort of move that away because we're not interested here in actually measuring the building of the pipeline. And then the next thing that we have to do is we can sort of think of, well, what could actually in real life scenarios influence the raw execution throughput of the pipeline? And in our case, I was thinking about, well, actually the pipeline, because it's dynamically composable, it can actually have, it has a pipeline depth. And what I looked at is what are common cases sort of how deep can a pipeline actually be, came up with numbers like 10, 20, and 40, and added sort of these as sort of permutations to sort of the execution benchmark to actually make sure that we sort of look at sort of reasonable deviations of how deep the pipeline can actually be. But we have to be aware that about sort of the parameter and combinatorial explosion, right? Because the more parameters we add that can influence, the more we're sort of blowing up the sort of the execution time of the benchmark. And then again, we also might be skewing the results, so we have to be careful. I selected only sort of the pipeline depth as the single input parameter. And then the next thing that I usually do is when I'm still sort of in this sort of inner loop of sort of benchmark and improve, I usually add sort of the short run attribute because the short run, as it already says by the name, make sure it only does sort of a quick run. And then that is just to give me sort of a direction where I'm heading towards, right? To make sure that I'm heading in the right direction, because I'm not interested in the specific time to get like a fully statistical result. I just want to look that I'm heading in the right direction. And then at the end, I add sort of the actual pipeline execution. Here we can see the before, it's the pipeline before the optimization, it's the baseline of the benchmark, and then I compare it to one of the approaches that I sort of execute, and then I run this benchmark. I'm not going to show you the benchmark results because that's also not relevant for this talk. If you're interested, you can run the code yourself on the repository that I will share towards the end of the talk. Then the question is, what is actually a good benchmark? So usually a good benchmark, it should follow the single responsibility principle. So as sort of all other methods should be doing, it means a single benchmark should cover a single thing. Like I've shown you, the execution benchmark, it only actually sets up the pipeline and it executes the pipeline. And it also sort of does the parameterization of how deep can the pipeline be. But that's all it does. It doesn't do any other scenario coverage. And then a benchmark should have no side effects. And that's really crucial because the benchmark is going to be, after the global setup has run, it's going to do a bunch of iterations. And if every iteration sort of mutates some state that then influences other iterations, that's not a good benchmark. And for us, we're just setting up the pipeline, executing it over and over again, but there is no sort of mutating state in there, so it has no side effects, so it's a good benchmark. Then another thing that's important, we should make sure that it doesn't do any sort of dead code elimination. So that means, because sometimes when code is not used, the cheat looks at it and says, oh, this code is not used, I'm going to compile it away. And then you're in trouble because you're actually measuring nothing, right? So we need to make sure that we use, for example, we return stuff with BenchmarkDotNet, or we use the consumer class that is available in BenchmarkDotNet to make sure anything sort of intermediate results are actually consumed by our benchmarking infrastructure, so that the cheat doesn't optimize it away. And then usually use a good framework like BenchmarkDotNet that sort of delegates all the heavy lifting to the framework. So for example, with BenchmarkDotNet, it doesn't require you to do a number of invocations per iteration, because what BenchmarkDotNet does, it runs sort of a pilot experiment stage based on some iteration time setting, and then it does some statistical analysis, and it runs sort of the benchmark until the results are stable. So all that is sort of abstracted away by the framework for you, and you don't have to sort of think about these sort of edge cases. And then what's also crucial for a benchmark is always be explicit. So basically the code that you're writing, that you're seeing in front of your eyes when you look at the code, should be the code that is actually executed. So no implicit casting should be in place, no vars. Make sure you declare the stuff that is there, so that you don't have sort of surprising side effects because some implicit casting operators in place that you're not seeing in the code, and then it skews your result. And then this is might be obvious, but sometimes when we're running benchmarks on our infrastructure, on our sort of laptops or workstations, right, we forget that we should make sure that we have the benchmark has dedicated resources. So you don't want to run a Zoom webinar or a Teams meeting at the same time when you're actually running benchmarks, because that's going to skew the results as well. So avoid doing that. Good. Now, I highly prefer BenchmarkDotNet because it sort of abstracts lots of things away for you. So for example, it runs the benchmarks in separated processes. So it applies sort of process isolation so that any side effects are sort of out of the window. It makes sure that sort of it applies smart heuristics based on standard error and runs the benchmarks multiple times until the results are sort of stable, right? That's also super nice. So that sort of measurement errors are sort of reduced, the likelihood of measurement errors. And really, BenchmarkDotNet was sort of designed to make accurate benchmarks with as repeatable results as possible. And it's a very good library, because at the end of the day, what Benchmark also does, it sort of removes outliers, because sometimes you have measurement errors that would sort of skew result, and it removes those so that you have sort of a good statistical baseline, right? And at the end of the day, is even for people that have been doing benchmarking optimizations for a while, benchmarking is really hard. And you want to use a library that protects you from the common pitfalls that does most of the dirty work for you, so that you can just focus on the actual problem that you're trying to solve. Then again, so far we have only covered sort of the execution throughput in relation to the pipeline depth. Another scenario that is also relevant for the pipeline execution is that we need to sort of measure the warm-up scenario. Why is that important? Because from the design choice perspective, the pipeline does some expression tree compilation, so it sort of builds everything together, and that code takes time. And we want to make sure that we're super fast also in serverless environments, that we're not in the way, right? So the warm-up of the pipeline is also a scenario that we need to take into account. So we want to make sure that when we're changing, improving the pipeline, and potentially even the expression tree compilations, then we're sort of not making things worse. Or when we are making things worse, we want to know whether it's within the thresholds that is acceptable, because we're sort of making the trade-offs between warm-up and execution speed and all those things. So this is what I've done in that benchmark that I've just showed you. And the next thing is that we have to look at what are other scenarios that we could sort of take into place. So most of the time, it doesn't really make sense to sort of test code that throws, right? Because I told you it's not a unit test. So a benchmark shouldn't really care about exception cases, because we would be benchmarking sort of the performance of throwing and catching exceptions. And again, throwing exceptions should be exceptional, and exceptions should usually not be used for the control flow. So most of the time, you should not be benchmarking exception cases. But here, for us, the picture is a little bit different, because when the pipeline is sort of executed in a message-based system, it is possible that, for example, a user code has an error, it throws a null reference exception. And then, because we're handling thousands and thousands of messages concurrently, it could happen that we're actually throwing an exception, right? So, and in that specific case, we're moving sort of lots and lots of messages, potentially after a series of retries, we're moving it to the error queue for further processing when actually the problem that was occurring in the system was resolved by, for example, deploying a patch. And so what we can derive from that, for us, sort of exception cases are actually a regular case, and we need to test for it. And that's what I did as well. So I created another benchmark besides the warm-up. I created a benchmark that looks at the exception cases. And this is how it looks like. So essentially, the input parameter is still, there is a pipeline depth, because how deep the pipeline is also influences, depending on sort of where the exception is thrown, how the performance is happening, right? Because essentially the exception bubbles up the whole call stack and then eventually gets handled and the message gets moved to the error queue. So what we're doing here is we're sort of taking the pipeline the depth, and then we're adding to the lowest point in the pipeline, we're adding sort of a behavior that throws an exception. And that's how we tweak sort of the execution benchmark, or we add another iteration of a benchmark. So that's the better description. And then what I'm doing is simply, I'm doing sort of a before, where I sort of do a try catch to make sure that the pipeline actually executes. And then I do a try catch with the optimized version, and I do a before after comparison of these two optimizations that I'm looking at in the exception case. Good. Maybe you have noticed the name step 1, step 2, and step 3 in the previous screenshot, because essentially this is coming from sort of the act that I've been going through the extra mile of making relevant things pluggable, sort of a partial class and methods in sort of the base infrastructure in that pipeline folder that you see here on the screen. And what this allowed me to do is I essentially had a few sort of optimizations in my mind, and I wanted to compare them against each other. So I tweaked sort of the pipeline, that the copy-pasted sources with partial methods and classes, and then I extended those in the step 1, step 2, and step 3 folder with various iterations of the things that I had in mind, right? That's what I've done. And if you're interested to see how that looks like, in the repository that I'm sharing towards the end of this talk, you can actually see this in code. If you want to benefit from what I've done there, you can actually look at the repository. Good. And now, once we have sort of done all that, we essentially want to make sure that the things that we actually have improved something, right? So what I'm doing there is then I take sort of, after doing all these benchmarks and the iterations in the inner circle, when I'm reasonably certain that things are working, I potentially have done not just the short run, but the long run to actually do the comparison. I've then put it back into the test harness that I wrote at the beginning to get an understanding of the full picture of the context that I'm looking at with the memory and the CPU profilers. And I've done that. I really sort of have a private version of sort of answer bus with the pipeline, and then I bring it back into the harness. And here on the screen, we can see a before and after. So on the message session publish, previously we had sort of 453 megabytes of allocations. We had sort of this behavior chain allocations, and after my optimizations are there, we can see it in the harness that essentially the behavior chain allocations are gone and lots of other allocations are now visible. But we achieved the pipeline optimizations that we were looking for. Then we can also look at sort of the receiving end, right? Because that's also an important part of the picture. And we can see sort of from 653 megabyte of allocations, we went down to 596 megabyte of allocations, and the func of behavior context of task on the left side is now gone. On the right side, and other allocations are sort of popping up now. And then when we sort of compare again the stack trace side by side, On the left side is the before, on the right side is the after. We can now see that previously had all sort of this infrastructure garbage in place. We can now clearly see on the right side that we have mutate incoming transferred message behavior, and then we just have the async state machine, and then the next one is mutate incoming transferred message behavior, then unit of work behavior, and all that stuff is sort of optimized and gone. So again, we see what we want to see. Then what we also can do is, again, we can sort of filter into the pipeline namespace on the before and after. Previously, we had a bunch of allocations, and now we filter in the after. We can see that the pipeline namespace is no longer allocating lots of garbage. So we also achieved something there from an allocation perspective. But again, because we always have to look at both sides, memory and CPU, we can now look at the CPU characteristics. And again, we look at the flame graphs as sort of a before and after. And when we saw the previous flame graph had lots of infrastructure parts in there, then when we zoom into sort of the optimized version, now we can see that the flame graph starts lighting up sort of the orange parts, and we can start seeing how the JSON serialization is now in there. We can see that the actual business logic that is executed in there, and all the infrastructure part is gone. So now, by just looking at the sort of the flame graph, we already have a good indication of where things are heading towards. And the same is actually also when we look at sort of the flame graphs on sort of the receiving end, where we have this receive with transaction scope that we have before. When we are zooming in, we can now again see that there is a better sort of ratio between the red parts and the orange and yellow parts. And the flame graphs clearly indicate sort of how all the bloat that previously has eaten up 32.3% of the publish operations and 40% of the receive operations, they're all gone. And that's a big win from sort of a performance improvement standpoint. Okay, then the next part, I'm going to very quickly fly through this in the interest of time, but I just want to sort of get sort of the point across that you can take this sort of a loop, the performance loop, and you can apply it to various parts of the stack. So for example, I talked to you that I've been using MSMQ and it has sort of a diminishing user base, but what we can actually say is that the transport has sort of a significant impact on the throughput of the system with answer response, and that's a crucial part. So for example, we can look at the customer distribution and we could say, well, Azure Service Bus might be a transport that is more often used, right? And then we can, for example, go and we can set up a test harness for a system that is using Answer Bus with Azure Service Bus, and then we can look at the before and after picture of using a system that is using Answer Bus. And don't get shocked. I'm gonna quickly fly over it because really the code is not that important. It's more about sort of the process that I'm going through. With Azure Service Bus, because I had a hunch something is not optimal with the SDK and was actually creating lots and lots of allocations and slowing the system down, I actually created the test harness that is here. And I'm using now the same scenario that I did with Answer Bus, but I'm using the Azure Service Bus SDK. And what I'm doing here is basically, I'm publishing or sending 1,000 messages to Azure Service Bus, and that's this gist here. Again, you don't need to understand this code, but I'm just sort of publishing to Azure Service Bus 1,000 messages, and then I'm receiving 1,000 messages. And at that time, I already had a hunch that potentially the problem with the SDK is that when I access the byte array that I'm getting from the service, will sort of allocate every time I access, and that actually significantly slows down the throughput of the system. And when you then attach the profiler, what you can then see is now, because we are sort of deeper down the stack, we can now see that things are lighting up from the Azure Service Bus SDK, and the Azure Service Bus SDK underneath has an AMQP driver. And now we can see lots and lots of allocations that are happening there. And in my specific point, because I accessed the body multiple times, we can see we have 5.6 megabytes of allocations of array resize. And after sort of contributing to the Azure Service Bus SDK, we were then able to sort of reduce the number of allocations, half the numbers of allocations by tweaking the Azure Service Bus SDK library, and sort of with the virtue of that sort of contribution, making the whole Service Bus ecosystem using for all the customers that using Azure Service Bus way faster. Good. That's sort of, as you can see, is you can apply this loop over various sort of iterations over the stack, and looking at various pictures, whether you go sort of breadth first or you go depth first, that depends on the application domain that you're looking at. Let me quickly talk about sort of, I showed you this approach of copy pasting source code. And I said it's a little bit controversial, right? Because this approach only really works when you sort of have code that doesn't change that often. But sometimes if you're going down the path of doing more sort of performance optimization and you want to become more performance aware, you want to make sure that sort of subsequent iterations of making changes to the code are not regressing your code base, right? But what you can do is there is actually a great tool. It's called and great guidance written by Microsoft in this links that I will share towards the end. It's preventing regressions, and you can then use sort of the result compare tool to essentially do a before and after. So what you do is, in essence, you take the code, you run the benchmark, and you sort of store the artifacts into sort of a disk folder that you run against the code that is not yet optimized. Then you run the same benchmark and you store the artifacts into an after folder. And then what you use this result compare tool to essentially measure the before and after and define a threshold. And if the threshold is above a certain percentages that you define or above certain values, then you can, for example, fail the build pipeline that you have in place. But about the build pipeline, when you use this approach, there's actually one thing that you need to take into account before you go down this path. And this is essentially when you're executing stuff on your build pipeline, you need to have dedicated hardware, because usually, for example, things like GitHub action runners, they're actually too unreliable to execute regression tests. So Andrei Akinshin has written a great blog post about the performance stability of GitHub actions. And sort of, as you can see here on the screen, the gist of it is that 2 subsequent builds on the same revision can have ranges of 1.5 to 2 seconds and 12 to 36 seconds. And CPU-bound benchmarks are much more stable than memory disk-bound benchmarks, but the average performance levels still can be up to 3 times different across builds. So as you can see, is with sort of this copy-pasting approach, I have shown you a very pragmatic approach to get started to become more performance aware. And then once you go down sort of the path of reliable builds, so reliable benchmarks, regression testing on your build infrastructure, there are more things that you have to take into account, but at least now you have heard the things that you have to consider. Now I'm at the sort of the wrap up of this talk. So what I have done here, I have shown you sort of the pipeline, sort of the performance optimizations, right? And you might be thinking, but how is that relevant for my business code? Well, although I showed this pipeline, I truly believe that these optimization techniques and the performance loop that I've showed you is also relevant for your business code to optimize it and to get a better understanding of what's going on. And then you can use this performance loop and the tricks that I've shown you today to sort of isolate components, profile, change profile, with a sort of breaking existing behavior, then rinse and repeat to become more performance aware. And then you can sort of also combine it and bring it back into the test harness to become sort of to do a macro benchmark to see how these small changes start adding up over time. And then what I also advise you to do is start optimizing existing things until you hit the point of diminishing return, because I truly believe that exploring sort of the ins and outs of an existing code path until you cannot further optimize it is actually gives you tons of great insight that you can use to redesign at a later stage, at a later point in time, and create a new design that is optimal based on the things that you have learned. So I have here a QR code. The first one, the green one, leads you to the repository that is also here, github.com/Daniel Marbach/beyond simple benchmarks. I have a second QR code on the screen. Should you wish to get sort of my help to sort of get a better understanding of your distributed systems with messaging, I can help you there as well. And before I go to the questions, I want to mention that because I'm in good contact with JetBrains, I actually can do a raffle. So if you reach out to me over one of the above contact details and tell me which is your favorite slide and what you got from it, or provide me structured feedback about this talk until the end of tomorrow, that's Friday, you'll be included in a raffle for a personal JetBrains Ultimate license, which contains all the JetBrains tools, including the ones .trace and .memory that I have shown here today. Okay, that's it. Now I'm heading over to a question. Let me just read them. The first question is, do you have a CI setup for benchmark so that when changes are done, you get feedback if perf was degraded? If so, can you share some resources, how such things can be set up and best practice around the setup? I've shown you that in the talk, right? So there is the sort of the result compare tool from the .NET performance team that you can download. I have the links in the slides that we will share, and then you can use that. Be aware of the blog post that Andre actually wrote about sort of the unreliability of things like DevOps Runner and GitHub Actions. So you need to have dedicated hardware for that. I've answered that. And the other one is when benchmarking optimizations and the results show decrease in memory allocations, but degradation of performance, do you have a ratio and or consideration to make a decision whether improvements are actually improvements? That's an excellent question. And it's very hard to answer this question actually specifically, because it's a generic question. I can only give a generic answer, but we would need to look at sort of the specific examples. But sort of the essence there is that, again, the context of the code, right? If you sort of are maybe in a sort of memory constrained environment, you might be willing to sort of trade off the throughput or performance there, but you don't want to spend more memory, right? So depending on your needs, you can actually go and say, you know what, I'm actually happy with that. I can live with less throughput in this specific example, or with warming up scenarios like I showed with the pipeline. You might be saying, well, it's okay to spend a few more milliseconds sort of on the warm-up time because we can do other tricks in a serverless environment to speed up things that sort of compensates for that, but we want to make sure that we're faster at execution time. So again, you have to balance these things depending on the context or the application or the business code you're working on. Good. I think that's more or less it from a questions perspective.
Daniel, hey, it's Kylie.
Yeah.
It looks like we got one more question that popped up.
Yeah, so using BenchmarkDotNet, do we have any limitations to look for a longer run? I'm not sure I understand that question. So I guess I'm going to do an interpretation of the question. So again, for me, it's really crucial when I'm sort of in this iterative mode of doing performance optimizations. I want to see that if I'm heading in the right direction, I do short runs. Once I'm reasonably certain, I'm doing a long run. And then I'll take into account that it takes half an hour, 20 minutes, an hour, depending on the scenario, to run it, to actually see that I'm getting a statistically relevant result that I can then share. So that's what I'm doing. But again, you always have to sort of balance, right? Again, the how much time you invest, how statistically significant should it really be? Sometimes it's just, I just want to prove to my colleagues that it actually improves things, then maybe a short run is good enough. Again, it depends, your mileage may vary. So that's sort of the approach that I'm taking. Hopefully that answers that question. Thanks, Kylie, for reminding me about that last question. Good.
Yep, no problem.
That's it from my end.
All right. Well, thank you so much, Daniel. And our colleagues will actually be speaking at a number of events this month in Sweden, Poland, Florida, and Belgium. So if you're interested in any of those, go to particular.net/events and find us at a conference near you. That's all we have time for today. On behalf of myself and Daniel, goodbye for now and see you on the next Particular Live webinar.